Thank you. Thank you for coming for the annual Cecilia Payne-Gaposchkin lecture. It's worth reminding ourselves from time to time just how astonishingly large a difference Cecilia Payne-Gaposchkin made to astronomy. And in her PhD thesis, where she brought modern quantum mechanics and statistical mechanics to the study of the atmosphere of the sun and stars, led to the realization that the diversity of stellar spectra was more a reflection of differences in temperature and, to a lesser degree, surface gravity, than differences in composition, which were what was suspected at the time. Also led her to the astonishing conclusion, then astonishing, that the atmosphere of the sun was predominantly made out of hydrogen. Whereas people had reasonably extrapolated from their knowledge of the composition of the Earth to think that the sun was likely made out of similar material. One of the leading astronomers of the age, Russell, persuaded her not to make much of this conclusion until he was able to reach the same conclusion himself a few years later. And there was a certain degree, rather substantial degree of injustice at the time, but time, I think, and a historical view has made clear that it was actually in Cecilia Payne's PhD thesis that first reached this landmark conclusion. So in the interest of time, I'm not going to go through the rest of the history. It's an extraordinary history of Cecilia Payne and then later Cecilia Payne-Gaposchkin here in Cambridge, including being the first full professor in the FAS who was a woman. So let me turn to our speaker today, Fiona Harrison. And all institutions have mythologies about themselves, especially strong institutions, and we're no exception. And one that we often hear, and that I often repeat, especially to potential donors, is that pretty much anybody who is anyone in our field has spent some significant portion of their career here. Fiona's an exception. It's amazing that she's managed to do so well. Fiona was educated at Dartmouth College and then at Berkeley, and then went straight to Caltech, where she stayed. And she's progressed up through the ranks and has made a very successful career with only occasional visits to the East Coast. But remarkably, after a considerable amount of scientific effort and engineering design work, and frankly, NASA soap opera, she became the principal investigator of NuSTAR, which we're going to hear about today. So with that, I think I'll hand the floor over to Fiona Harrison.
Thank you. Thanks. So it's a tremendous privilege to be asked to give this talk in honor of such a great astronomer, and frankly humbling as well. And since NuSTAR launched in mid-2012, we've done a huge, vast array of science. And I was trying to think, what should I highlight in this talk? And of course, it had to be something to do with stars. Now, NuSTAR has looked at the sun, but I don't know anything about solar physics, so I decided not to talk about that. But what I will talk about is I will talk about what NuSTAR has taught us about the engines, the mechanisms that make massive stars explode. And I'll talk about the exotic endpoints, compact remnants of stars that we've used both to probe the galaxy and to learn about some exotic physics. And also, then I'll end, if I have the chance, by talking a little bit about supermassive black holes. But I'm mostly going to focus on stars. So NuSTAR is the first telescope that is able to focus high-energy X-rays. So when I say the X-ray band, I'm referring to photon energies between 0.1 and 100 kiloelectron volts. And as you know here, of course, in Cambridge, the Chandra Observatory and XMM Newton are flagship observatories that have revolutionized our study of the low-energy X-ray band between 0.1 and 10 keV. NuSTAR is a small explorer. Now, people ask me, what's small? Small is 160 million for everything, including launch and science, okay, which sounds like a lot if you work on the ground, not if you work in space. And it focuses in the energy range from 3 to 79 keV. And as the first focusing mission, it has improved our sensitivity by factors of several hundred, our ability to resolve the high-energy X-ray sky, and also it is able to make spectra. So it's not like we've never had high-energy X-ray telescopes before. Of course, many of you are familiar with missions like Integral and Swift-BAT. These are telescopes that operate on the principle of a pinhole camera. So you basically cast a shadow onto of a opaque and transparent mask onto a detector, which resolves this. And they're terrific for measuring, for studying gamma ray bursts, very wide fields of view, bright sources. But because you take the entire background of the detector into every pixel in your image, and detector backgrounds limit our sensitivity in this energy range, the sensitivity is limited. By going to focusing, where you actually reflect the light, bring it to a focal spot, so you can have a large area of optic, small area on the detector from which you're integrating background, you can get these vast improvements in sensitivity. So, as Charles already alluded to, it's been quite an effort to get NuSTAR into orbit. Being able to focus at these high energies took a lot of technology development, both new kinds of X-ray detectors we developed in my labs, new kinds of X-ray optics, and basically many of the parts of the instrument were built by a small team of collaborators around the world. So it was about 15 years from the first serious technology development to launch, and about 4 years actually building the mission. Here's the spacecraft and instrument all integrated at Orbital Sciences in Dulles, Virginia, where we put the instrument together with the spacecraft. We then drove it across the country, put it in the shroud of a rocket, which is a very unusual rocket called a Pegasus. That rocket then gets mounted under the belly of an L-1011 aircraft. Some of you may be old enough to remember the L-1011. Here is the, just focus on this. This is the shroud in which the entire payload has to fit, okay? And it's a fraction of the length of this airplane, all right? And then the airplane took off, flew to the Reagan test site in the South Pacific, where we launched from. Plane goes up to 30,000 feet, drops the rocket, okay? It ignites 5 seconds later and launches in front of the plane. Okay, so it's rather unusual. I happen to be friends with the CEO of Orbital, now Orbital ATK, who said, I will give you the rare privilege of riding on the plane for the launch. But I thought, being on a plane with a ton of solid explosive was not so appealing. So I was at UC Berkeley, where the mission operations took place for launch. Now, I was not so worried about the launch, because I figured, you know, the rocket will go up or it'll go down, and it'll be over very quickly, and nothing I can do about it. But what I was worried about was what had to happen 9 days later. So this gets back to that small shroud, fraction of the length of the airplane, right? And if you noticed on the second view graph, Chandra and NuSTAR are about the same length. Okay, they both have 10 meter, 33 feet focal lengths, so about the length of a school bus. So how did this happen? Well, so 9 days after launch, we took this structure with tens of thousands of piece parts all stowed away in this canister that we referred to as the trash can, And it deployed piece by piece, locking into place, all right? And this took 24 minutes. So this was my 24 minutes of terror. So I always tell my friend John Grotzinger of the Mars Science Lab that, his 7 minutes is nothing. I also knew that this had not ever been tested fully assembled on the ground. But it worked perfectly. We were everything locked into place. We got the requisite 10-meter separation between the optics and the imaging detectors. I'll just note there's 2 optics. They focus on 2 corresponding focal planes. We just co-add the images. We just do this to get more collecting area. Because it'll be interesting for the science later, I'll just point out that there are consequences of flying a slinky where you should have an optical bench. And in fact, things do move around on orbit. And so we have 2 lasers here and a star tracker that are constantly measuring the relative orientation of the 2 benches so we can correct the photon positions on the ground. And I'll just say that forced us to design detectors that don't integrate, that measure the arrival time, the energy, and the position of every photon. And that's turned NuSTAR into a wonderful pulsar discovery machine. And I'll talk about that. Because I'm here at CFA, among many Xray astronomers, I'll just point out, here is the collecting area quantitatively of NuSTAR. This is Xray energy, 100 keV. And this is Swift Chandra XMM. You can see they all cut off just because of the design of the optics at 10 keV. NuSTAR extends significant collecting area up to a cutoff in the optics at 79 keV. And again, X-ray astronomers will understand these units. They're not important. Just note, this is the sensitivity for these pinhole camera type instruments measured in milliunits. NuSTAR sensitivity is measured in microunits. Okay? And for the optical astronomers, smaller is better. Okay, so just to show you qualitatively what a big advance NuSTAR has made, I compare here the coated mask integral telescope image of a region about 1 degree by 2 degrees centered on the heart of the Milky Way, Sagittarius A star here. And you can see that about half a dozen bright point sources can be resolved. 1 pixel in this image, all right, is the NuSTAR field of view, which is about 12.5 arc minutes. All right, the resolution is about 1 arc minute. And here is NuSTAR's image above 10 kiloelectron volts of the heart of the galaxy. This is where the supermassive black hole, Sagittarius A star, is. You'll note here there is true diffuse emission aligned with the plane of the galaxy, and we're, for the first time, resolving diffuse knots. Now, this diffuse component has a very hard spectrum. It's a new discovery, and I'm not actually going to talk about it. It's about 4 by 8 parsecs on a side. It's a subject of a paper that just came out last month in Nature. We don't really understand what it is, all right? But it may be the collection of remnants of stars that are accreting in modes that we don't understand. It's certainly very puzzling. Again, I'm not going to talk about it. I'll just point out it's always interesting what the media picks up when you publish a paper. But the Galactic Center has been an interesting place since NuSTAR's launch. And I'm going to focus on one of the significant results from the observations of the Galactic Center. So just for context, to remind you, here's an infrared picture of the Milky Way. And of course, there's so much dust and gas that the nucleus of the galaxy is obscured by many magnitudes of extinction in the optical, but visible in the radio, submillimeter, and X-ray. Again, here's NuSTAR's image. And that supermassive black hole at Sagittarius A star, which has, 4 million times the mass of the sun, is very underluminous. It's only 500 times the luminosity of the sun, 10 to the minus 9 times Eddington, all right? So it's very wimpy. But every sort of once a day, it will flare with getting 10 to 100 times brighter, and then the flares fade away after about an hour. And you see these also in infrared. And we got very lucky. We actually looked at the Galactic Center shortly after launch, before we were completely done commissioning, and detected one of these large flares. And I'm also not going to talk about that. What I am going to talk about is observations we made in April of 2013. Now, some of you may remember all the hype about this gas cloud, this so-called gas cloud that was going to hit Sagittarius A star, and everybody was all excited because, we know that the nucleus of the galaxy has been active in the past and is dim now. This might light it up. You might create an accretion disk. All sorts of things might happen. Of course, it's not entirely clear it's actually a gas cloud, but never mind that. There was all this excitement. People were monitoring intensively the Galactic Center. And on April 25th, there was a burst from a wide field Swift telescope, a burst of high-energy X-ray seen, and then Swift looked with a low-energy X-ray telescope and found a bright X-ray source coincident with Sagittarius A star as far as they could tell. So this triggered everybody to say, oh, the gas cloud is hit, right? There's this bright X-ray source, which was persistent. And so we thought, okay, we'll look with NuSTAR. This is exciting. And we did. And one of our postdocs, I'm not quite sure why, because black holes don't pulsate, but he said, well, I'll just do a pulsation search. And what did he find? From this source, coherent pulsations with a 3.7 second period, right? And of course, this means this is not a black hole, but it's what is it? It's the remnant of a star that is pulsing, and because of the high rate of spin down, the dipole model would tell us it has a high magnetic field. So this is a magnetar, a new magnetar, and Chandra then was able to look and see that this magnetar was offset from the Galactic Center by only a few arc seconds, projected distance of 0.1 parsecs, all right? And so very close to the black hole. And so the excitement was that maybe this is actually in a bound orbit around Sagittarius A star, and we can measure the effects of general relativity if we monitor over time. But unfortunately, timing analysis showed that this is not a stable pulsar like you would need. So this was really interesting. Why am I highlighting it as one of our premier results? Well, magnetars are very rare, and finding a new one is exciting. We think they result, they're young neutron stars with high magnetic fields, were born at a millisecond, spin down very quickly, and they have some dynamo mechanism makes tremendously strong magnetic fields. And just the detection of this one, I always love it when things are inferred from a sample of one, but made some papers be written about how the Galactic Center was a special environment for the production of magnetars. But really the most important aspect of this discovery was that this object turned out also to be a radio pulsar. And it's been a holy grail to find a radio pulsar near the Galactic Center, because radio pulsars can be used as probes of the medium between the pulsar and between us. And I'll just remind you what those probes are. Radio waves get dispersed, right? So the delayed as a function of frequency by ionized material along the line of sight. So there's a dispersion measure. And this has the highest dispersion measure of any known pulsar. There's also, when radio waves travel through a magnetic field, the plane of polarization rotates, and the amount of rotation depends on the strength of the magnetic field along the line of sight. And so this can be probed, can be used as a probe of the magnetic field strength, all right? And this has the highest, this is a highly polarized signal, I should mention, in the radio. So they were able to measure the rotation measure, and it has the highest rotation measure of anything except other than Sagittarius star. And there's also effects of angular broadening due to multipath effects, scattering of the radio waves, which both make the source appear larger and also broaden the pulses. And this pulsar has the same angular broadening as Sagittarius A star. However, it's much lower than previous models suggested might be the case. So why is this interesting? Well, the magnetic field measurement, this rotation measure, the inference, and this was work done by Effelsberg and other radio telescopes, were able to infer that, well, first, you need an ordered magnetic field. So this shows there's an ordered magnetic field, and it must be close to Sagittarius A star, two arguments I won't go over in detail. And so in this magnetized hot gas feeding Sagittarius A star, there's a magnetic field greater than 8 milligauss. And if you just compress this down, you get very high magnetic fields near the event horizon. And this is one of the ingredients that's required to make jets from the black hole, as perhaps seen by Chandra, and also to explain the very low luminosity accretion. Okay, so let me go to my second highlight. I'm going to talk about our first journal cover. This is the Sedona Journal of Emergence, which one of my postdocs found browsing in Vroman's bookstore in Pasadena, because the astrology section is next to the astronomy section. Okay, and he said, "Wait, that's NuSTAR's press image of the supernova remnant Cassiopeia A." And if you can read this, I'll read it for you. It says, "This new view of the historical supernova remnant Cassiopeia A, located 11,000 light years away, was taken by NASA. Inside, Cassiopeia speaks through Robert Shapiro." Now, what Robert Shapiro says, I don't know because I didn't read the article. But at any rate, Cassiopeia A is the closest young supernova remnant to Earth. And so it is one of the objects that is studied in order to try to understand supernova explosions and their remnants. And I'm going to tell you what we learned uniquely with observations with NuSTAR. So let me just remind you the standard picture we tell our graduate students about the explosion of massive stars. You have a massive star, 8 to 10 or more times the mass of the sun, and it burns nuclear fuel to the point where you have an iron core and then this onion layer structure of elements. And when the iron core gets to the Chandrasekhar mass, it collapses, and the material around it falls onto the protoneutron star, and you get a shock wave, right? So the inner part gets compressed to neutrons, and then you get a shock wave that travels out, okay, and is supposed to explode the star. Now, we know in the many spherically symmetric models, all spherically symmetric models, the shock stalls, all right? And something has to re-energize it. So some source of energy must get pumped into that shock to reinvigorate it and get it to explode the star. Now, one problem with this, we think that this mechanism has many people think that this mechanism has something to do with neutrinos, which are produced in copious numbers released by the protoneutron star in the interior of this explosion, that energy gets partially absorbed and reinvigorates the shock. But Dave Arnett likes to call it the famous non-explosion of supernova models problem, that You take all the best cross sections and you simulate this, and it doesn't successfully explode the star. So, however, recent advents of 2 and 3D simulations that are able to put in effects like turbulence and acoustic instabilities have found that if you have large-scale convective turbulence and other sorts of what I will characterize as low-mode instabilities, you do get successful stellar explosions. And this is a model by Christian Ott and his group, where you can see this is a simulation. Here I'll just point out this is the time in milliseconds. All right, and you'll see here is the stalling of the shock. So the shock that's supposed to explode the star stalls, and then he's introduced this large-scale turbulence, all right, which has 2 effects. You do PDV work, okay, so that helps explode the star, and you also have the material longer in the so-called high-gain region where you effectively absorb neutrinos. So this is a explosion driven by neutrinos that is successful, but that invokes these low-mode instabilities. Now, I love showing this because I'm an experimentalist, okay? So there's other types of, besides turbulence, instabilities. This is an acoustic instability. This is a dish of water with water streaming, okay, onto a region where it's deeper, all right? And you can see the development of what's called a standing accretion shock instability, okay? Now, whether this actually works in stars, it's, I think, a matter of debate. Nevertheless, this is another kind of low-mode instability that you can only simulate in 3 dimensions. That, again, has the effect of making it easier to explode stars. However, this is not the only kind of model that theorists are working on. There are many attempts to model rotate sort of emission going out in 2 directions, all right? And so if you could somehow get a picture of the shape of the core of the explosion, you could get information about whether these low-mode instabilities are operating or whether these, what I'll call more jet-driven explosions, are operating. So, again, one big difference in these models is the level of asymmetry. So, one can put constraints, however. Now, all of this is, the explosion itself is, of course, too small to resolve and is all over in milliseconds, so there's no hope of actually imaging the explosion itself. However, there are remnants left over, visible hundreds to thousands of years after the supernova that glow. They glow in the X-ray. And and so by studying the shape of the remnant, you might hope to constrain the shape of the explosion and say something about which theoretical models are correct. So I just want to remind you what we're seeing when we look at a supernova remnant. Here's the star with its onion skin structure. You have the explosion. And then this is a different shock. Okay, this is long after what you have a forward shock plowing the interstellar medium. You have a reverse shock that the material traverses, and it gets heated. Okay, and it gets heated to millions of degrees where it radiates in the X-ray. And this is a Chandra image of Cassiopeia A, all right, in different colors or different elements. And so you might say, well, look at this X-ray glow and see what the shape of the explosion was. Well, here's 2 Chandra images of Cassiopeia A. One in iron, okay, which is produced near the core of the explosion. One in the ratio of silicon to magnesium. And if you looked at this one, you would say it looks, if I had to compare it to one or the other, I'd compare it to the low-mode instability, right? I look at this one, I would say it's a jet-driven explosion. So what's going on? Well, as I just showed, what Chandra is seeing is only the material that has traversed the reverse shock and is heated. So there's all this material inside that hasn't been shock heated yet that you're not seeing. And also, the distribution is therefore very sensitive both to the structure of the very outer layers of the star, okay, and also that what happened, the mass loss that happened before the explosion. So you're not really seeing what happened in the core. Now, nature has provided us a perfect tracer of the core of the explosion that NuSTAR can see. All right, and this is in young remnants, so younger than a few hundred years old. So you not only shock heat material, but in the explosion itself, you create unstable elements, radioactive material. And this radioactive material will decay over time, changing one element to another. And the tracer that nature has given us that's particularly important is called titanium-44, which is produced, as it turns out, right at the dividing line between what falls back onto the compact star and what gets ejected out, the ejecta. Okay, so this is really tracing the core of the star. It's also, what happens is titanium decays to calcium, emitting gamma rays, two of which are in the NuSTAR band. So this radioactivity, you see whether the material is hot, cold, dense, thin, right? You don't have to have heated material. So this is a unique tracer of the shape of the core of the explosion. Oops. So here's the NuSTAR image of Cassiopeia A in titanium in blue. Okay, the green is Continuum Emission from Chandra. And you can see there's no real hint of elongation along any axis of any kind of bipolar jet-driven explosion. And in fact, we've worked with Chris Fryer and his group to do modeling both of the nucleosynthesis and these instabilities. And really, the shape that we see of the titanium is a strong indication that these low-mode instabilities were operating to explode the star. Now, I will say, I was told by a number of theorists before launch that NuSTAR observations of titanium would be a nice confirmation of what we already know, because the iron and the titanium are produced in the same place, and so we'll just have titanium. We'll get a titanium map that just matches Chandra's iron map. So here's the titanium in blue, here's the iron in red. Okay. So I asked my then 6-year-old daughter, are they correlated? She said, don't be ridiculous. So this is still a bit of a mystery, I have to say. We're not quite sure we understand it, but that's always a good thing about doing new observations. I will say I'm not going to talk about this too much, but in Supernova 1987A, which is another young remnant, which NuSTAR can't spatially resolve, but we can do a spectroscopy of these titanium lines. So this was a sort of watershed explosion. The light reached us in 1987, and first detection of neutrinos, basically confirmed basic ideas about core collapse. And this is a cleaned up Hubble image. You see these ring structures, but that's the shock interacting with the material that was ejected from the star prior to the explosion. That's not really mapping, again, the asymmetries. We just had a paper come out last week in Science where we reported, here's the titanium lines from 1987A as measured by NuSTAR. Here's the rest frame energy. And you can see there's a systemic redshift. So this means most of the ejecta are moving away from us, which means any any neutron star would have to be moving towards us, right? And this fairly significant 1,000 kilometer per second systemic redshift, again, means that you don't have one of these jet-driven bipolar explosions. You probably have something that is more like these large-scale turbulence models. Okay, so now I'm going to switch from the engines of massive stellar explosions to another result. And this result we got when we were looking at a type 1A supernova. So this is the thermonuclear detonation of a white dwarf, not the collapse of a massive star in M82. So supernova 2014J is a sort of once-in-a-century event. It's a 1A that occurred very close, only 3.5 megaparsecs from the galaxy in the Cigar galaxy. And this was detected in January around, I think the first detection was maybe the 15th or 16th, 2014. And one of the things we built in the primary goals of NuSTAR was to look at 1As after the explosion to try to constrain the explosion mechanism in 1As. All right, so we looked at this as soon as we could, and we stayed on it for about 2 weeks. Okay? And I'm also not going to talk about that. What I am going to talk about is the ultraluminous X-ray sources that we also happen to be in the field of view as we were staring at M82. So the supernova, I think, is somewhere over here. This is a Chandra image of M82. Chandra is the only telescope, so here's a plug for high angular resolution, that can resolve 2 really bright ultraluminous X-ray sources in M82, which are creatively called ULX1 and ULX2. All right, and I'll tell you, so ultraluminous X-ray sources, what's ultraluminous about them? Well, their X-ray emission is ranges between sort of 10 to the 39 to 10 to the 41 ergs per second. So this is very high for an accreting source. They are off the nucleus of the galaxy, so they're not associated with supermassive black holes in galaxies, all right, because they're spatially offset. And the big question has been, what are these ultraluminous X-ray sources? Are they, everybody has focused on black holes because black holes can produce higher luminosity because they have a deeper gravitational potential. And so the question has been, are these black holes that are accreting from a companion in the standard way that 10 solar mass galactic black holes accrete in our galaxy, but they just are scaled up versions with high mass? Or is there some mode that is causing them to look brighter because they're actually accreting just above the Eddington rate, but the accretion disk becomes very geometrically thick and the radiation is collimated, right? So this has been the question. And let me just remind you, of course, that we know of, in our galaxy, of stellar mass black holes up to a few tens of stellar masses. Here, ULXs range from 10 to the 39 to 10 to the 42. So if you're at Eddington, this is sort of Eddington for 10 solar masses up to 10,000 solar masses. And so there's been a lot of debate about the nature of ultraluminous X-ray sources, always focusing on black holes. So we had a program with, this is a little off topic, this is not from the observations of M82, but we did have a program in the prime mission to look at some bright ultraluminous X-ray sources. So bright, I mean, in this range, sort of 10 to the 40 to few 10 to the 40, so well above the Eddington limit for a neutron star. And what we found is the spectra, by and large, look very distinct from accreting black hole binaries that we know of in the galaxy. So here is energy, 10 keV, 1 keV. This is a nu F nu, both of these plots. This is a spectrum from accreting galactic, sort of 10 solar mass black hole, where you see, and I'm not going to go into details of why, but you see a spectrum that either has a peak at 1 to 2 keV and then falls off, or is very hard, what NuSTAR finds is the peak is at much higher energy, if you sort of fit this with a thermal model, and consistently fall off at high energies. And this is a spectrum similar to what you would expect in one of these very high accretion rate thick disks, because you get a lot of Compton scattering. And again, I don't have time to go into the details. And we looked at a large sample of these, okay? And here's just a rogues gallery. And you can see broadly they all look quite similar, all right? They all have this peak around, 8 to 9 keV, fall off with energy. There's some differences for sure, but by and large they look completely distinct from accreting, okay? Are super Eddington accreting stellar mass black holes, or I should say, I hate the term stellar mass because it's really 10 to 30 stellar, but stellar remnant black holes. So we were excited because we had this 2 weeks of data on these two extreme ultraluminous X-ray sources in M82, and we wanted to do spectroscopy to try to compare to that rogues gallery that I just showed you. Now the problem is that these two sources are 5 arc seconds apart, as I've already said, and NuSTAR doesn't resolve them. This is the NuSTAR PSF here. So this is a Chandra image that was taken February 2nd to 4th, coincident with when NuSTAR was looking at this field. All right. So we beat our heads on the data analysis for a long time and decided it was difficult to do with the spectroscopy because these were both sort of equivalently bright. At the time, both were around 210 to the 40 ergs per second. So we decided to resort to timing analysis. And one of my postdocs said, who's absolutely fixated on, postdoc on our team, fixated on timing analysis, said, I'll look for quasi-periodic oscillations, which you might expect from a black hole. But what he saw, similar to our result from the Galactic Center, was coherent pulsations. Here's the pulse profile, very sinusoidal. Okay. This is just a light curve showing you the pulsed flux as a function of time. All right. 1.37 seconds. As we know, black holes can't give you coherent pulsations. So we also noted that the period was changing during the observation, and the pulsed flux alone is 510 to the 39 ergs per second. Now, I won't go into the details, but we were, through a pulse-on, pulse-off analysis, able to associate that with the ULX2 source, which at the time, the total luminosity as measured by Chandra was 210 to the 40. So here's a 210 to the 40, 1 solar mass, roughly, compact object. All right. Now I'll note that there's also, we detected the binary orbit, 2.5-day modulation, extremely circular. And we can put some limits. It's extremely circular. We don't see eclipses. So we can put a limit on the companion mass. And it is spinning up erratically, which tells you, you have to have accretion to spin up the star from an accretion torque. So the model is that you have some disk, and then the material gets funneled along the magnetic field lines, falls onto the star, and you see the pulsations, of course, because the rotation axis is misaligned with that magnetic axis. Now, how bright can this model get you? Well, like almost anything in my field, most things were discussed by Rashid Sunyaev and someone else in the 70s. I guess they tried to stay out of trouble and go do calculations. But they were interested in this question. This basic model where you funnel material along the magnetic field, so you get some kind of accretion column here, right? And the magnetic field is strong enough to make that stiff, okay? And then you can exceed the Eddington limit because the radiation comes out the side, right? So you don't have the radiation stopping the accretion. And they confidently predicted the maximum luminosity you could get was 10 to the 39 ergs per second. Okay, because above this, right, what happens is this material here at the base gets very hot and you start losing energy to neutrinos. And anyway, this is 210 to the 40. So I think Rashid should go back to doing high-energy astrophysics and tell us what's going on. But I will say this is one of my highest citation rate papers, besides the NuSTAR instrument paper, because, you know, this is interesting. So many papers immediately appeared on the archive, so saying that this was, you know, a magnetar with a very high magnetic field, and you could exceed Eddington because you suppress the Thomson scattering. It confidently predicting it's a low magnetic field neutron star and an unusual high mass X-ray binary, and therefore a new channel for millisecond pulsar formation, and implications for studies of gravitational waves and formation of black hole binaries, because of course this isn't going to last very long as a neutron star if it really is accreting at 10 to the minus 5 solar masses per year, right? Or that it's a pulsar with a standard magnetic field like we just saw the model for. But none of these models explain all the observations, which you have a very sinusoidal pulse profile. So you don't have a lot of beaming, okay? So this really is high luminosity, very circular orbit, and this spin up. So what's going on? Well, I'll say that there is hope that we'll understand a lot more about this system, because we would like to look and see whether this system, if it's persistent and really accreting, or is it more transient. Can't we have a hope to detect evolution in the orbit and in the spin-up? And so hopefully the Chandra TAC will agree with us and approve our monitoring program. But I just want to leave you, okay, with a summary, because this can be kind of confusing, right? I first told you ULXs are black holes, then I told you this one's a pulsar. What really are they? Well, so both. I think there's strong evidence for these super Eddington accreting stellar mass black holes from the NuSTAR spectra, all right? Also, I'll say this one, X1, there's been a recent paper, I'm not entirely sure I 100% believe it, but that found QPOs in a 3-to-2 ratio that says that gives you a 400 solar mass black hole. I won't go into the details of why, but at any rate. So, and there are some ULXs that have luminosities well above 10 to the 41, up to 10 to the 42. So there is at least one compelling case for an intermediate black hole. So we have a very diverse, interesting population here. And since I have 5 minutes, I'm just going to sneak in one supermassive black hole result, because it's recent and I think it's quite interesting. And that's a result that we got when we were looking at an object, highly luminous, supermassive black hole that has evidence for a wind of particles from its disk. So let me just remind you that there's evidence from the X-ray that in some luminous objects you get particle winds from the disk. And these winds are naturally expected at high accretion rates. And the evidence is, if you look at the X-ray spectrum, and this particular one I think is an XMM spectrum, this is Markarian 509, you see an absorption line. And if you associate it with highly ionized iron 25 or 26, then that gives you outflow velocities of some fraction, 10, 20, 30% of the speed of light. Now, this is very interesting, of course, because we know that there is some feedback mechanism in quasars where the black hole is affecting things on galactic scales. And so the question is, how powerful are these winds? Now, that's hard to tell if you just have an outflow velocity, right? Because to really tell how much mass is flowing out, you need to know the solid angle, how wide are they? You can't get that from a single absorption line. The column density, which you can get by doing modeling of the photoionized gas. The energy, that's easy. The launch radius, which you can constrain from the ionization state and escape velocity. But the big question is, you don't know the solid angle. And so you can only infer it from looking at how many luminous X-ray quasars and AGN have these lines, and I would say that is pretty dodgy. Some people find lines everywhere they look, other people don't. So this is really an open question. Now, if the outflow really is large angle, close to spherical, right, then you would expect that you would see, here's the observer, here's the outflow, you'd expect you'd see blue shifted, absorption blue shifted, but also on the red side, emission, right, from the material going away from you. And this gives you what's called a P Cygni profile for the people who are familiar with this, which says that, in a large outflow, you might expect to see red and blue shifted absorption, red shifted emission. And so we decided to try to see whether NuSTAR could detect these absorption features by looking at a nearby AGN called PDS 456. So this is the most powerful radio quiet AGN in the local universe. And here is a spectrum from, again, I think this one is, I can't remember if this is XMM and Suzaku, but anyway, this is from Reeves et al., 2003, where in this source you see very strong blue shifted absorption around 10 keV. Now I want you to notice, both in this and Markarian 509, you're not detecting any emission on the other side of the absorption feature, right? Just because the energy cutoff is of these soft telescopes is 10 keV, right? Now, I will say in this source, sometimes you see two lines, and so you can confidently get a velocity for the outflow of around 0.3 C. So we decided to look jointly with XMM and NuSTAR in a campaign of 5 observations. And what we found is that if you have NuSTAR, the points in orange, and XMM, right, you notice first, just forget the line, and look at this continuum. You see how it's turning over and changing dramatically right at the upper edge of the line? Right? That's because if you have an outflow, you have a high column, which means you're going to have absorption. You'd expect columns 10 to the 23, 10 to the 24, which give you this kind of curvature in the continuum, which you could not measure. And so if you have both, you see, you fit it, and you get a beautiful P Cygni profile. Here's the red shifted emission. Here's the blue shifted absorption. So this was published in Science this year. And so this is the very first convincing constraint of the wind geometry at greater than 2 pi steradians. And I won't go into this because I'm running out of time, but in this campaign, the comforting thing to me is, again, some of these line detections are, I would say, not convincing, but we see the same profile in each of 5 spaced out observations. We see variability in the continuum. Line profile is always the same. Anyway, we can get some very interesting numbers from this, all right? So if you put in this 2 pi steradian outflow, and from the variability and other modeling, a launch radius of around 100 gravitational radii, you find 0.2 times the bolometric luminosity in the outflow, all right? And this means if the wind lifetime is anything significant, persistent 10 to the 7 years, the energy released through the accretion disk exceeds the binding energy of the bulge of the galaxy. Okay. So this is, now, the big theoretical question is, does this wind energy actually couple to the galaxy and do anything? All right. This is somewhat open, but I will note a very interesting recent result on IRAS F11119. This is an artist conception. This is a ULERG where Herschel has detected massive molecular outflows. All right. And with Suzaku, there is the tentative detection of an ultra-fast outflow in the Xray. Now, the problem again here is to get this profile, what they don't tell you is they had a observation with a non-focusing high-energy instrument on Suzaku called the PIN, which had a weird excess, and they fit this, and then they see this absorption line. So I would say it needs confirmation, but this would be the first system where you actually see, because we approved this for a NuSTAR A01 guest investigator program. And so I think this will actually nail whether this feature is correct or not, because we can get the true continuum just like we did in PDS 456. I shouldn't say we anymore because it's somebody else. But it's also interesting to note what the public found interesting about this press result. Anyway, I don't make these things up. No responsibility. So anyway, we've had a lot of fun with NuSTAR. Again, we launched in 2012. We celebrated the second birthday in 2014. Here are astronomers around the world celebrating, and I have to point out, much of this work is not mine, but many results from a very talented team. I will note on the second birthday I was visiting Cambridge, England, and so it was the afternoon, and so we had champagne. Everyone else just had coffee. But at any rate, many collaborators here, Francesca Giovano, Martin Elvis, Josh Gridley, Laura Lopez, so I should visit more often, and as Charles said, get a little culture. But we're now going to get we've got 2 years approved for a guest investigator program. Proposals due in November if you would like to write one. And so I hope there's lots more fun to come. Thank you.
Thank you. So talk is now open for questions.
Well, the ULXs, so the spectrals are being fed at a very high rate, presumably from the companion star.
Right.
Do you have constraints on the orbital parameters?
So we don't. There are some constraints. So the problem with the companions is they're in very crowded regions near the nuclei of galaxies, and it's very hard to isolate a companion. There have been some cases where a companion has been isolated, and in one case where there's a claimed measurement even of a Doppler shift in the companion line, but
You don't get variability from it?
yeah, so it's very, very. We've tried this with Keck to get spectra and go after the variability, and we haven't succeeded. It's very, very hard because they're crowded, typically a lot of absorption, so you're doing this in the infrared. But that is a holy grail if you could go after some of these and really get constraints on the companion and the mass.
Ramesh?
So this ULX that turned out to be a pulsar. So as you said, it's one of those two objects in M82, ULX1 or ULX2. Now presumably Chandra has the spectrum of each of these individually, at least up to 8 keV. So is there anything in the spectrum? Is one of these guys looking very weird, or they all look just like the others?
Yeah, so let me explain a little bit why we think that it's ULX2.
Sure.
So what we were able to do with NuSTAR, even though the full impact max is only 18 arc seconds, by taking pulse off, pulse on minus pulse off, we registered the pulse off position, right, with the Chandra image, and then we could see the with other sources in the image. And then we could see the position shift from X1 to X2 on off. So that makes us associated with X2. In the Chandra band, there's not a lot of difference in the spectra. Now, they're highly absorbed, so you don't have a lot of bandwidth. But, however, we're now trying to do the pulse-on, pulse-off spectroscopy with NuSTAR, and there is evidence of a much harder cutoff spectrum that looks more like, accreting pulsar than like the ULX spectra that I showed you. So but it's tough because they're so close. Now, again, if our Chandra proposal is approved, what we hope to do is find a time from the Chandra monitoring when X1 dominates, get a spectrum, and then when X2 is on, and get another spectrum, and I think we'll get it from that.
And you can say that none of the other ULXs is a pulsar?
No. Well, okay. We've done timing analysis, and we don't detect pulsations, but no, I can't confidently say that. I mean, the thing is, these pulsations are also somewhat transient. During some parts of the observation, they appear to get weaker. Actually, similar to SMC-X1 does that, and perhaps be undetectable. So we can't say confidently, but I actually think from the broadband spectroscopy, that's really the clincher, that sample that we looked at that all have those similar, very similar spectra that are consistent with, you know, what you might expect from a High-Eddington disk. They probably are black holes, but I won't, and after this, I'm not going to swear anything.
So, also for the same objects, is there any sign of the pulsations in the Chandra data?
There's not. Now, part of the problem is that you need to have the Chandra in a timing mode, right? Because they're sort of 1 second pulsations, and so there isn't. We looked in the archive, and there's no data that's in an appropriate mode that we could go search for them. So, and we've also looked in archival XTE data. We couldn't see anything. Now, XTE, of course, integrates the entire galaxy, but it's a good timing machine. And we haven't been able so far to detect anything.
Cool.
Have you seen any cyclotron features in any galactic sources?
We have, actually. So there are a number of papers that you can look up. What we've been trying to do, so cyclotron lines, for those who don't know, are, you have a high magnetic field, 10 to the 12 Gauss, you get scattering from between Landau levels, and you get these cyclotron resonance scattering features, which are in the high energy X-ray band. And yes, what we've been trying to do is correlate them with the luminosity of the source, which tells you something about the height they're produced at. There's a theory that if you're at lower luminosity, that height is higher, and you expect to see variation in the line strength as the shock moves up and down. And then at high luminosity, shock's closer to the surface, and you wouldn't see that. So we've been trying to test that model. But yes, there are quite a few sources now where we have very nice measurements of the cyclotron lines, and harmonics, actually, as well.
All right.
Well, just a quick question. Go back to the beginning of your lecture when you're inside the galaxy.
Yes.
Towards the center. You deduced from the rotation measure the strength of the magnetic field, and I was wondering how you disentangled the electron density from the magnetic field, since it's the integrated effect.
Yes. So let me just be clear. I didn't actually do that. That was work by Edenow et al. That was published in Nature, the radio observations. And they go through an argument, see if I can reconstruct it, that it has to be local because, how does the argument go? It has something to, okay, I'll have to look up the paper again. You can read the paper, but it has something to do with associating the column, well, okay, I actually can't remember exactly what it is, but it is a somewhat complicated argument. But I think it's fairly compelling, was my conclusion, that it has to be within, a few tens, 0.1 or 0.2 parsecs of the Sagittarius star, that ordered field.
Let's thank our speaker again.